Right now, as we speak, 3I Atlas, an enormous glowing object the size of Manhattan.
For one thing, 3I Atlas, as it's called, is interstellar, meaning it's from outside Earth's solar system.
The James Webb Space Telescope had been trained on a faint, icy wanderer from interstellar space when something utterly unexpected unfolded before its mirrors. Astronomers observing 3I Atlas, only the third known interstellar object to pass through our solar system, suddenly noticed a brilliant flare that wasn't supposed to happen. The readings showed an abrupt surge of infrared radiation, a bloom of heat expanding like a miniature sunrise against the dark. Webb sensors, sensitive to the faintest whispers of thermal energy, captured the moment when something gigantic struck 3I Atlas, a collision so improbable that it sent shockwaves through the astrophysics community. Before we start, please don't forget to like and subscribe to our channel for more updates. The images streamed back to Earth in near real time were mesmerizing. A small, distant blur that had been moving with measured calm suddenly erupted into chaos. Plumes of vaporized material unfurled from its surface, scattering fragments across the void. It wasn't just a minor impact. The energy release suggested that the object colliding with 3I Atlas was immense, possibly the size of a large asteroid or even a small moon. For something that had traveled for millions, perhaps billions of years between stars, untouched by any planetary body, to suddenly meet such a fate within our neighborhood of space seemed almost poetic in its rarity. What the James Webb Telescope recorded in those minutes became one of the most significant events in modern astronomy. The collision was so luminous in infrared wavelengths that it temporarily outshone nearby stars. Instruments tuned to detect thermal gradients registered a steep spike, indicating that temperatures at the point of impact rose to several thousand degrees Kelvin. That meant ice, silicates, and organics on 3I Atlas's surface were instantly vaporized. As the expanding cloud cooled, Webb's spectrometers began dissecting the light, revealing the chemical fingerprints of elements never before detected in interstellar debris. Scientists had long speculated about the nature of interstellar visitors. The first, 1I/Oumuamua, passed through quietly, enigmatic and fast. The second, 2I/Borisov, was more comet-like, releasing gases and dust. But 3I Atlas was unique even before the collision. Larger, slower, and with an unusual reflective surface that suggested metallic content beneath its crust. Its arrival had already generated excitement, but when Webb caught it in the act of colliding with something massive, it transformed from curiosity to cosmic revelation. What could possibly have hit it? The initial theories varied wildly. Some thought it collided with a large Kuiper Belt object lingering at the edge of the solar system. Others suggested it met another interstellar fragment, perhaps traveling in a loosely bound cluster. The sheer energy implied by the flare suggested that the impactor was no small rock. Estimates placed it at tens of kilometers across, moving at several tens of kilometers per second. That kind of kinetic force would have been enough to shatter even a solid iron body. Yet the debris field that followed showed that part of 3I Atlas might have survived, now fractured and tumbling, still glowing faintly in the infrared spectrum. Webb's observations began to outline the geometry of the explosion. Dust plumes extended for thousands of kilometers, spreading in a cone that mirrored the direction of impact. Each plume contained finely grained silicates, carbon compounds, and exotic ices, substances that could only have formed in the cold recesses between stars. The infrared glow revealed carbon dioxide, methane, ammonia, and complex hydrocarbons. These weren't ordinary molecules. Some bore isotopic ratios unseen in any solar system material. It was as if Webb had opened a window into another galaxy's chemistry. The event demonstrated the telescope's power beyond anything yet recorded. Where older instruments like Hubble could only have seen a faint sparkle, Webb's infrared eyes resolved the physics of destruction in exquisite detail. The layers of the interstellar traveler peeled away like pages in a book, each layer telling a story of its birthplace. A distant stellar nursery where elements fused in ancient suns. The shockwave from the collision vaporized those pages, but the resulting spectra preserved their content. For astrophysicists, it was a cosmic autopsy performed by light itself. The implications for planetary science were staggering. Until now, interstellar objects were studied from afar as silent messengers of other star systems. But this collision turned one into an active laboratory. The vaporized material gave direct clues about how planets might form elsewhere, what ingredients make up distant cometary bodies, and how organic molecules endure across the gulfs of interstellar space. For decades, scientists had wondered whether the building blocks of life could drift between stars, carried on icy bodies like 3I Atlas. Now, they had a chance to examine those blocks firsthand, freed by the violence of impact. Every major observatory on Earth turned its gaze toward the event. Radio telescopes captured echoes of the explosion, the expanding dust clouds scattering microwaves in unpredictable patterns. Optical telescopes detected a faint halo growing around the impact site, while spectrographs on Webb continued to monitor the shifting emission lines. Within hours, computers around the world were modeling the trajectory of debris, tracing back the origin of the impactor. Some simulations suggested that it might have been a rogue object ejected from the Oort cloud, while others hinted at a body entering from interstellar space in parallel with 3I Atlas. The idea that two travelers from different star systems had met in a collision was both statistically improbable and profoundly awe-inspiring. Astronomers began to realize that the collision was not merely a freak accident. It was a message from the deep time of the universe. Every interstellar fragment carries a signature of its origin. The metallic fingerprints of the stars that forged it, the isotopic memories of ancient supernovae. When two such objects collide, their combined spectra create a tapestry of chemistry spanning multiple stellar generations. Webb had recorded such a tapestry in progress. The data, when decoded, would not just tell the story of the collision, but of entire star systems long vanished. For days, the debris continued to glow, cooling slowly. As the heat dissipated, Webb's instruments picked up crystalline patterns forming within the dust cloud, structures that hinted at the recondensation of minerals under microgravity. This was cosmic creation and destruction interwoven. Elements that had been locked in ice for eons were reborn as microscopic silicate grains, potential seeds for future worlds. The same processes that shaped planets billions of years ago were unfolding before human eyes, replayed in miniature against the velvet dark. What fascinated scientists most was the diversity of compounds liberated by the impact. Among the expected ices and silicates, Webb detected traces of polycyclic aromatic hydrocarbons, complex organic molecules thought to be precursors to amino acids. Their presence was not surprising, but their abundance was. The impact seemed to have triggered chemical reactions that reassembled simple molecules into more elaborate structures. It suggested that high-energy events in interstellar space might be catalysts for molecular evolution. This finding reverberated across astrobiology. If such collisions can synthesize complex organics in the void between stars, then the universe may be full of seeds waiting to fall into fertile environments. The old idea of panspermia, that life's ingredients drift through space waiting for a home, gained new momentum. 3I Atlas, once an anonymous wanderer, had become a demonstration of nature's ability to recycle and recreate complexity even in destruction. The collision also shed light on the mechanical strength of interstellar bodies. Data from Webb and supporting observatories suggested that 3I Atlas was more cohesive than expected. Despite the impact's violence, parts of its core seemed to remain intact. That hinted at metallic bonding or sintering under cosmic rays over millions of years. It was a revelation about how matter behaves under prolonged exposure to interstellar radiation. Instead of fragile snowballs, these travelers might be compact reinforced relics, natural composites formed in alien environments. As the analysis deepened, a startling possibility emerged. The impactor itself might not have been natural. Some anomalies in its reflective pattern suggested symmetry, a consistent ratio of dimensions, and a thermal profile inconsistent with an irregular rock. It was premature to declare anything artificial, yet the whispers spread rapidly through scientific circles. Could the object have been a fragment of something constructed? A derelict probe? A remnant of technology from another civilization? Webb's data neither confirmed nor denied the possibility, but it forced researchers to consider that interstellar debris might include artifacts as well as asteroids. Regardless of its nature, the impactor's role was transformative. The collision had created a spectacle visible across multiple wavelengths. The expanding shell of gas now reflected sunlight, forming a faint ephemeral nebula, a glowing testament to an encounter between two travelers from beyond the sun's reach. Webb continued to document the evolving structure, showing filaments of material curling outward, sculpted by radiation pressure and microgravity. Over weeks, those filaments stretched into delicate arcs, like frozen ripples in space. The visual beauty of it captivated the world. Artists and scientists alike compared it to a cosmic flower blooming in slow motion. Each frame from Webb revealed new tendrils, faint colors shifting as molecules cooled and recombined. The collision had turned a fragment of interstellar debris into a transient nebula, a reminder that creation and destruction are intertwined across the universe. Even in annihilation, the cosmos creates new forms of elegance. Astrophysicists studying the event emphasized how it could redefine our understanding of cosmic dust and interstellar chemistry. The ejected material was likely to drift through the solar system for centuries, mixing with the local dust population. In time, some of those grains might fall toward the sun or be drawn into planetary atmospheres. Future generations of scientists might find traces of 3I Atlas embedded in meteorites, remnants of a collision that Webb alone had witnessed in its first moments. The discovery also tested the limits of current models of celestial mechanics. Collisions between interstellar bodies within the solar system were thought to be nearly impossible because of the vast emptiness of space and the extreme differences in velocity and trajectory. Yet here was proof that such meetings could occur. It implied that interstellar traffic through our system might be more common than previously imagined, and that our cosmic neighborhood is not as empty as once believed. Astronomers recalculated probabilities, and the results were sobering. If even one major interstellar body enters the solar system every few years, and collisions of this scale can occur, then the flux of material from beyond our star is far greater than expected. Each encounter becomes an opportunity for cross-pollination between star systems, a kind of galactic exchange of matter. Over billions of years, such collisions could homogenize the chemical makeup of the Milky Way, blending elements and molecules from countless origins. At the same time, Webb's findings challenged old ideas about the boundaries of star systems. The material composition of 3I Atlas, revealed in the post-impact spectra, bore traces of isotopes suggesting formation around a red dwarf star with a high metallicity, a very different environment from our sun's. The fact that such material now floated through our solar system, illuminated by human instruments, underscored the interconnectedness of the galaxy. The Milky Way, once seen as a collection of isolated systems, appeared more like a vast ocean of migrating fragments. The precision of Webb's instruments allowed scientists to reconstruct the event's timeline with extraordinary fidelity. Infrared cameras recorded the initial flash lasting only seconds, followed by a cooling phase spanning hours. Spectral lines showed that the vaporized elements recondensed into microcrystals within a day, forming shimmering dust clouds. In that brief interval, a process that normally takes millennia, the breakdown and reformation of matter, had occurred in real time. The collision became a condensed version of cosmic evolution, a microcosm of how stars and planets recycle their ingredients. The observatory's mid-infrared instrument revealed something even more intriguing: traces of magnetic alignment in the dust, suggesting that both objects carried remnant magnetic fields. Such magnetization could only arise if their parent systems had strong stellar fields, or if the bodies had once orbited magnetically active stars. If both interstellar travelers originated from magnetized environments, their encounter might represent a meeting of magnetic relics, cosmic fossils still echoing with the electromagnetic memory of their birthplaces. Beyond the scientific fascination, the discovery stirred a profound philosophical reflection. The collision was a reminder of how, even across unfathomable distances, the universe remains dynamic and unpredictable. Two objects that had traveled alone for eons, separated by light years, met by chance in the shadow of our sun. It was a momentary alignment of cosmic trajectories, an event both violent and beautiful, accidental yet deeply symbolic. Humanity, observing through a mirror of gold and silicon orbiting far from Earth, happened to witness it. For researchers at the Space Telescope Science Institute, the event represented a turning point. Webb had fulfilled its promise not only as a window into the distant universe, but as a sentinel watching the happenings in our own cosmic backyard. Its sensitivity allowed it to act as both explorer and witness, chronicling phenomena that had once been invisible. The data streaming in would occupy scientists for decades, each wavelength a clue to the physics of collision and the chemistry of interstellar evolution. The fragments of 3I Atlas, now spreading outward, were cataloged carefully. Some pieces reflected sunlight in faint periodic flashes, suggesting rotation or tumbling. Others emitted steady infrared radiation, their surfaces still warm from the impact. Tracking these fragments offered insight into how debris evolves under solar radiation and gravitational influences. The paths of these remnants would become a living experiment in orbital dynamics, demonstrating how interstellar matter interacts with the gravitational web of our solar system. Even the way the light faded carried information. Webb sensors recorded subtle oscillations in brightness, thought to be caused by spinning shards reflecting the sun in rhythmic pulses. From those flickers, astronomers derived shapes, densities, and compositions. Some fragments appeared metallic, others icy. A few exhibited spectra unlike any known natural mineral, prompting speculation about exotic compounds formed under interstellar pressures. Each data point expanded the vocabulary of cosmic materials. Among the most striking revelations was the detection of deuterium-rich water ice. The ratio of deuterium to hydrogen in 3Y Atlas's vaporized material was unlike that of any comet or asteroid within our solar system. It pointed to an origin in an environment colder and more distant from its parent star than any known protoplanetary disk. That discovery alone could redefine models of planetary formation across the galaxy, suggesting that water, the essential ingredient of life, forms under far more varied conditions than once thought. Long after the initial flare had faded and the immediate frenzy of observation subsided, the scientific community remained transfixed by the data streaming from the James Webb Space Telescope. The collision that had shattered 3I Atlas had become more than a single astronomical event. It was a key to understanding how matter, momentum, and magnetism weave together across the interstellar void. Even as the debris dispersed, Webb continued to detect faint, lingering heat signatures that revealed how the fragments interacted with solar radiation and the background plasma of interplanetary space. These whispers of energy carried stories of chemical rearrangement, radiation-driven transformation, and dynamic forces that operated on a scale no laboratory could reproduce. One of the first puzzles scientists faced was the pattern of motion exhibited by the debris. The fragments didn't drift evenly as expected from a simple collision model. Instead, they showed an oscillating motion that hinted at residual charge or magnetic interaction. Some of the larger shards appeared to repel or attract each other subtly, forming temporary alignments before breaking apart again. That strange choreography suggested that the impact had ionized parts of both bodies, leaving them electrically active. Theories emerged proposing that such charged fragments might act as seeds for magnetic dust storms that ripple through interstellar space. If confirmed, this would indicate that collisions like the one Webb recorded help maintain the galaxy's magnetic balance, injecting charged material that keeps vast cosmic fields alive. The delicate balance of forces within the debris field fascinated theorists. Simulations showed that if even a small fraction of interstellar collisions produced charged particles in this way, then the Milky Way's magnetic web could be continually refreshed. It meant that events once considered insignificant, rare impacts between ancient wanderers, might be vital to the long-term dynamics of the galaxy itself. For the first time, astrophysicists could connect the behavior of microscopic dust grains to the macrostructure of cosmic magnetism. Webb had not only observed a single dramatic event, it had inadvertently opened a new window into the hidden electrical architecture of space. At the same time, chemists working with the spectral data began to identify transient compounds formed only during the collision's brief inferno. Molecules like cyanopolines, which require both high energy and extreme cooling to form, were detected in concentrations never seen in comets or nebulae. These molecules are fragile and fleeting, yet they play a central role in the chemistry of carbon chains that lead toward life's organic complexity. The collision between 3I Atlas and its unknown impactor had momentarily created the perfect crucible for their synthesis, a furnace followed by a deep freeze. The violent act of impact had imitated on a small scale the early environments of planetary formation where heat and shock sculpt raw matter into potential life-bearing compounds. For planetary scientists, the event offered a living experiment in creation through chaos. It demonstrated that destruction in the cosmos is often a prelude to new chemistry. The vapor cloud, stretching thousands of kilometers wide, was more than debris. It was a reactive zone, a transient atmosphere in which elements that had never met before suddenly collided and bonded. Carbon, oxygen, nitrogen, and silicon swirled together in turbulent flows, forming molecules that would have been impossible to make under static conditions. As Webb observed this evolving chemistry, it became clear that interstellar collisions could be catalysts for the molecular diversity seen throughout the galaxy. The expanding cloud also provided new insights into how light interacts with complex dust. Observations in the mid-infrared showed peculiar polarization patterns, tiny asymmetries in how light waves were scattered by dust grains. Those patterns allowed scientists to estimate the shape and alignment of particles smaller than a micron across. Some were smooth and spherical, but others had jagged geometries that scattered light unpredictably. The diversity of shapes hinted that 3I, Atlas's interior, had undergone cycles of heating and freezing before the collision, perhaps from past close passes near other stars. It was a record of thermal history preserved in the texture of dust, like tree rings in cosmic form. Every telescope that could point in the right direction joined the investigation. Even small ground-based observatories tracked the dimming fragments to refine trajectory estimates. The data revealed that not all the debris followed predictable paths. A subset of particles appeared to be moving faster than could be accounted for by the initial explosion alone. They seemed to have been accelerated post-collision by electromagnetic forces within the expanding plasma cloud. This unexpected acceleration suggested a kind of self-generated propulsion, a miniaturized analog of the processes that drive astrophysical jets from young stars. For researchers studying plasma physics, it was a chance to see those same principles at play in a controlled natural experiment. As weeks passed, Webb's sensitivity continued to extract detail from what was now little more than a fading wisp. One of the most intriguing findings was the detection of an unusually strong emission line associated with ionized titanium. That was surprising because titanium is not typically abundant in icy bodies. Its presence implied that deep within 3I Atlas lay a metallic core or embedded inclusions of heavy elements. Such metals could only have formed in the aftermath of supernova explosions. The interstellar traveler, it seemed, had carried within it remnants of a long-dead star, and the collision had finally revealed them. By analyzing those metals, scientists could trace 3I, Atlas's origin, back to specific types of stellar environments, perhaps even to a particular region within the galaxy. The more that was learned, the more the event's improbability grew. The odds of an interstellar body entering the solar system are astronomically low. The odds of such a body colliding with another object of comparable scale are lower still. Yet it had happened within the watchful eye of humanity's most advanced observatory. Statistically, it was like 2 grains of sand drifting in the Sahara meeting midair during a storm, and one of them being recorded by a camera 1,000 miles away. The sheer unlikelihood forced astronomers to reconsider how interstellar traffic moves. Perhaps the galaxy is more crowded with small dark objects than previously thought, invisible until they reveal themselves through catastrophe. In the months following the impact, the research community developed new models of interstellar object populations. The data from 3I, Atlas's trajectory, combined with the physics of the collision, hinted that it might have been part of a larger stream of debris, a river of material ejected from a distant star cluster millions of years ago. Such streams could periodically intersect the solar system, delivering both dust and larger bodies. If correct, that would mean our system experiences periodic influxes of alien material, enriching its chemical inventory and perhaps influencing the formation of comets, or even the atmosphere of outer planets. From a broader perspective, the event illustrated the dynamic interconnectedness of galactic matter. The Milky Way is not a static collection of stars and planets, but an ongoing exchange of materials moving between them. Each collision, each stray particle of dust plays a part in that slow, endless circulation. The collision seen by Webb was a glimpse into that process in fast forward, a vivid snapshot of the forces that recycle matter across the galaxy. For many researchers, the philosophical impact was as significant as the scientific one. The idea that our solar system had just hosted a collision between emissaries from two entirely different stellar nurseries gave a sense of cosmic unity that no theoretical model could provide. It was as if two ancient travelers born under different suns had met for a final embrace witnessed by distant observers capable of understanding what it meant. In that sense, the event transcended its physics. It became a moment of existential connection between humanity and the broader universe. Meanwhile, engineers studying the Webb data realized that the telescope's performance during the event had far exceeded its design specifications. The instruments had not only captured the flare, but continued to collect high-fidelity data, even as the brightness faded by orders of magnitude. That precision proved Webb's potential for monitoring fast-evolving phenomena. Plans quickly formed to adapt its observation schedules for transient tracking, making it the first interstellar collision early warning and monitoring system. If similar events occur again, Webb or its successors could catch them from the first microsecond. Deep space physicists began using the collision data to refine impact models for high-velocity bodies. They discovered that when objects travel at interstellar speeds, impacts generate exotic states of matter, plasmas dense enough to mimic the cores of planets. For a brief instant, temperatures and pressures during the 3I Atlas collision rivaled those at the heart of gas giants. Understanding those conditions could help explain how heavy elements fuse or separate during planetary formation. In essence, nature had created an experiment that revealed what happens when matter meets at relativistic boundaries of speed and force. The event also offered new insight into the stability of interstellar travelers. Before the collision, 3I Atlas had been under observation long enough for its spin rate and brightness variations to be recorded. After impact, the changes in those patterns showed how the internal structure responded to stress. Some layers seemed to flex before breaking, suggesting a stratified interior of alternating ice and metal. This structural complexity confirmed that interstellar bodies are not simple frozen chunks, but layered relics built through complex histories of heating, cooling, and accretion in alien environments. As the cloud of vaporized material spread outward, solar radiation began to sculpt it into intricate arcs. Observers noticed that the tails and filaments curved in ways inconsistent with simple solar wind pressure. Instead, the curve suggested a rotation of charged dust under an unseen field, possibly remnants of the object's combined magnetism. The realization that such magnetism could persist and shape debris on a macroscopic scale hinted at new physics in the behavior of charged grains in microgravity. In the grand scheme, those curls of dust may resemble the earliest patterns that once formed the first disks around young stars. There was also a subtler kind of data emerging from the collision, the way the light flickered as it passed through the dust cloud. This flickering, caused by microlensing and diffraction, allowed researchers to measure particle sizes with extreme precision. The results revealed a stunning diversity, from nanometer-scale metallic specks to millimeter-sized crystalline shards. Each grain, in its own way, was a time capsule. Some originated deep within 3I Atlas's core, while others were likely surface residues exposed to cosmic rays for eons. Their combined story painted a layered chronicle of exposure, migration, and survival through interstellar space. Among all these discoveries, one aspect stood out for its beauty and strangeness. The light echo from the collision, photons scattered by dust and bouncing across interplanetary space, continued to expand outward, forming a growing sphere of reflected light. Sensitive telescopes captured that expanding shell as it illuminated nearby regions of space like a ghostly ripple. For the first time, humanity could watch a literal light echo from an interstellar impact, a luminous memory of the moment when two travelers met. Those echoes, faint but measurable, provided a three-dimensional record of the event's geometry and timing, enabling scientists to reconstruct it with near-perfect precision. The consequences for the field of astrochemistry were enormous. Before this collision, most understanding of interstellar chemistry came from spectroscopy of distant clouds and comets. But 3I Atlas's impact offered a front-row view of chemistry in action. Scientists could track how molecular bonds broke and reformed under extreme conditions, providing invaluable data for refining reaction models. This information could apply to star-forming regions, supernova remnants, and even exoplanet atmospheres. It bridged gaps between laboratory experiments and the grand theater of space. In the weeks that followed, the idea of collision chemistry became a frontier topic. Researchers began hypothesizing that throughout the galaxy, countless small impacts between interstellar fragments might be quietly shaping molecular diversity. Each collision, though invisible from Earth, might spark bursts of chemistry that replenish the interstellar medium with complex organics. In this view, the galaxy is not a static collection of drifting dust, but an active ecosystem where collisions act as metabolic reactions on a cosmic scale, constantly producing, destroying, and redistributing the raw materials of life. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on the gigantic collision with 3I Atlas? We want to hear from you. Thank you for watching and see you next time.